So we continue with our discussion of quantum phenomenon, and now we're going to move on to the Heisenberg uncertainty principle, which I mentioned in the previous lecture. That in classical physics, if you know the initial conditions, you know at what angle, with what velocity this is going and where it starts, you can know where it's going to end up. But quantum says no, you cannot. That there is this limit, that this would represent the uncertainty in how well you knew where something was, and this would represent the uncertainty with how well you knew what it was doing, momentum, and the product of those two always has to be greater than h bar, which is Planck's constant divided by 2 pi, an unnecessary detail. I would push this further. Most people say it is a matter of your knowing, but I am certain that that is wrong, that it is a matter of reality, that it is not there is a limit to how precisely you can know where something is and what it's doing. There is a limit to how precisely something can be and have well-defined behavior. That you think about the models of the atom. I can go back there. That this statement, that this is the nature of reality, that is not because you looked at it, that there's a limit to how precisely you can know where it is and what it's doing. This is reality even when you are not looking. Okay, so that's very important to me. It's not that because you take measurements, because you look, that things become uncertain. Because you look and know where it is, that its behavior becomes uncertain. That is reality even if you don't look, that there is a limit to how precisely things can have position and momentum. Okay, so here is backing off from that a little bit, but it's a nice illustration. If you have light passing through a gap, it has well-defined momentum. It's traveling in nice straight lines, but I don't know exactly where it goes through that gap. If you make the gap narrower, it still has well-defined momentum, and I'm a little bit more precise about where it was it went through the gap, but still some uncertainty there. But if you make the gap too narrow, then suddenly you get this diffraction phenomenon where we become aware of the Heisenberg going on, that where it's passing through is such a low level of uncertainty that the uncertainty in what it is doing as it goes through there becomes very high, and you get the light going all over the place, not traveling in a nice straight line like it did there. So we send light or electrons. Remember that de Broglie suggested we could think of electrons as wave-like. At any rate, let's look at this wave behavior. You send radiation through double slits and you get diffraction and interference. Very strong wave phenomenon. But we understand that it's just a matter of probability, and the movie that you will see will make that very clear. It's a very important point, that this is actually the overlaying of probability functions, not the stuff coming through here. But enough of that. It turns out that if you send the photons or the electrons one at a time through the double slit, this experiment has been done many times, and you still get interference and diffraction. Now that is troubling. How can one particle, how can one electron interfere with itself? Well, maybe it's spread out. Maybe it has an ill-defined location. Maybe it's possible for it to go through both. Do you really believe that? Let's find out. how does this happen? That one electron sent at a time, reaching the screen, making a mark on the screen, and then the next comes along. How can you get an interference pattern? How can you get places where the electrons never go if they're only traveling one at a time? They don't have anybody else to talk to. Well, what we do in the experiment is we observe this slit here, and we are able to see what's going on, whether the electrons are going through both slits or one slit at a time. Turns out we find them going through one slit at a time. And when we look, the only change we made to the apparatus was we observed. We didn't touch anything. We just gained knowledge about which hole the electrons were going through. And the interference disappears. There's still diffraction, but no interference. There is the loss of this mechanistic reality. Our participating by just gaining consciousness, knowledge, changed the behavior. That this behavior was not independent of us, that us knowing changes the way the universe works. That is very bizarre. And again, the statement that I was making earlier, that until, this is the quantum understanding of what's going on that I would like you to have. When you didn't look, it is not that the electrons were going through one slit or the other. They were doing all possible things. That what we know is I started an electron out, and an electron reaches this screen at some particular place. But in between, I do not know what they are doing, and in fact they are doing all things. And that it is what you are seeing here is the overlapping of their probability functions for those all things that they are doing. And that one understanding of what happens when you look is you cause that multiplicity of doing all things between where you started it and the screen. And here when it gets to the screen, it is detected, it is observed, and so there it collapses to be just doing one thing, but you caused the collapse to happen here. Your observing caused the multiplicity that the electrons were doing to collapse to one reality of it going through this slit or that slit or hitting the wall. Okay, that observing causing reality is very troubling, and it led Schrödinger to propose this, which was meant to show that it's ridiculous to say that observing causes reality at a non-quantum scale, but people latched onto it and said, whoa, there is reality. So you got a cat in a box with poison, and there's some random event that either causes the poison to be released or not. And if the poison is released, the cat dies, and if the poison is not released, the cat stays alive. But the point is that what is going on before you observe? And the answer is that everything is going on before you observe. It is not that the cat is either dead or alive and you don't know it yet, but the quantum understanding would be that the cat is doing all things. It is both dead and alive, and it is 70% dead. I have no idea what 70% dead means, but the cat's reality is all possible things before you observe, and it is the act of you lifting the top and observing that causes this quantum collapse to the one reality that you find of the cat being alive or dead. Before you look, the cat is all things. Okay, that is the point I've been making. Next bizarreness. all things are possible if you do them quickly enough. If I take the statement of the Heisenberg uncertainty principle, I can multiply both sides of this and divide both sides of I can multiply and divide this by delta t, but delta p divided by delta t is force, and force times change in position is work, and work is transformation or change of energy, and so we get this alternative statement of the Heisenberg uncertainty principle, which is read the uncertainty in how much energy is present times the uncertainty in how long it has existed for cannot be smaller than Planck's constant divided by 2 pi. What that means is this. I have an electron, and I cannot claim that the electron has a location. It has a certain probability of being here, but it has a lower probability of being here and a still lower probability of being here, and vanishingly small but not non-existent probability of it being out here. And if the electron has those probabilities, then suppose it has 5% probability of being found out here. Then if you look at it 100 times, 5 of those times you will find it out here. Well, probably doesn't quite work like that, but if you worked at it 100 million times, no, 100 billion times, then 5 billion times you would find it here when you looked for it. Well, suppose there was some barrier that the electrons couldn't get past, absolutely cannot get past. The fact is that the probability function for where the electron is extends beyond that wall, and you will find it beyond the wall a certain percentage of the time. But how does it get there? It can't get past that wall. And what we say is that this is an energy barrier. You can't get past that without having enough energy to get past the barrier. And what the electron does is sometimes it has more energy than it has. It borrows the energy that it has no right to, and as long as it keeps it for a short enough time, it is sufficient for it to get out here. We say it tunnels the barrier, which is more like crawling under the barrier instead of going over it, but that's the expression. It's called tunneling, for it to get beyond a barrier that it cannot get past. Now, if this barrier were a bigger barrier, then it would have to keep that energy for a longer time, and the probability of it doing that would go down. But still, it would happen sometimes. When you built an electric motor, I told you to make electrical contact between the wires by taking the insulation off so that the electrons could move, and then wrapping the wires together. But the fact is, the instant you take the insulation off, scrape that insulation off, the copper wire oxidizes. And that copper oxide is an insulator. And it is not possible for electrons to get from one wire to the other wire because of that insulative layer. But it happens. How does it happen? It happens because the electrons tunnel that barrier, and they tunnel it very easily. They evidently have to borrow but a very small amount of energy to get past that barrier, and so it happens a lot of the time. The probability goes way, way up, and with certainty we could be confident that the electrons would flow from one to the other. There you go. That was quantum in your life. If you take a chunk of glass and you send light in at greater than the critical angle, then it is not possible for light to refract, to get out. If it's greater than the critical angle, then you're going to get total internal reflection. There is no logical possibility of it crossing that barrier. And yet, if you bring a second chunk of glass up small enough to make this barrier small enough, then suddenly you will see a beam of light. That it does the impossible. It tunnels that barrier. I don't know how it does it. It's quantum. Don't ask me to make sense of it. Radioactive decay involves a negative beta particle leaving the positive nucleus. That is not possible. There is an energy barrier that says, no, you are attracted to that positive. You're not going to go away from it. You're not going to have enough energy to get out of the nucleus. And yet, beta decay occurs because the electrons get more energy than they have for a sufficient time to get outside the nucleus. And that's why radioactive decay is a probabilistic event. You cannot say it's going to happen or when it's going to happen. You can just give the probability that given this amount of time, half of them will do it. I can't tell you which ones, but the probabilities are such that half of them will decay. When you get alpha decay from a nucleus, that's a matter of a helium nucleus separating from the other bigger nucleus. But they are held to one another by strong nuclear force. There is not enough energy for a helium nucleus to get out of the nucleus, but it does, because it borrows the energy and it gets out. So radioactive decay, again, is this borrowing of energy. The last thing for us to look at is the Einstein-Podolsky-Rosen experiment. Created by Podolsky and Rosen, Einstein put his name on it so people would pay attention, because Einstein had a battle with quantum. He didn't like that probabilistic quality, and so he thought it must be wrong, and he chose any excuse he could to try to find the holes in quantum. Einstein famously said, God does not play dice with the universe. And Niels Bohr responded, don't you tell God what to do. But Einstein just couldn't handle that non-deterministic, that probabilistic quality of quantum. So here's how the experiment works. An event occurs which gives off two particles. That there's this energetic event that creates these two particles. So energy has been transformed into matter. That's a relativistic effect. But these particles have spin. And spin is a property that has to be conserved. You take my word for it. So this one might have spin up, in which case this one would have spin down. And this one could have spin left, and this one would have spin right. That whatever spin this one has to have the opposite spin. But what spin does this have? Well, we don't know. That's the nature of quantum. It has all possible properties until we observe it. So it's spinning in all possible directions. Well, we allow these particles to move apart, maybe miles, maybe hundreds of miles apart, and then we send this particle through a detector. And depending on the spin, this magnetic field will cause it to turn in some specific direction. That is, we will observe to find out what spin it has. But the minute we observe, that's going to cause a quantum collapse. And at that instant, this one here must collapse to exactly the opposite. But how could this particle, separated by miles from this particle, know that this one had collapsed? How could it know how this one collapsed so as to collapse the opposite way? This would be faster than light communication between those two. And Einstein had shown that nothing, not even information, can travel faster than the speed of light. So this seemed to be a hole, a downfall in the quantum phenomenon. But instead, what his audience realized was it meant that these two particles were in fact never separated. they remained the same part. They remained quantum entangled with one another, and so they were not, in fact, separated by miles. And that is pretty weird stuff as well. Thank you, quantum, for weirdness. You think quantum is crazy? You're right. You think it's not real? You're wrong. In 2006, I had a website that suggested that 30% of the economy was on quantum based. You get rid of quantum, you have to get rid of lasers, solid state electronics, transistors. You have to get rid of magnetic resonant imaging, MRIs. You have to get rid of scanning tunneling electroscope. You can't check out of the grocery store using the laser scanner. It is so prevalent in your life. All the solid state electronics, all the computing that's done, and everything computes these days has a chip in it. It all goes away if you don't have quantum. It is beyond human understanding. Our brains cannot handle the reality of quantum, but there is no question that quantum is a reality. And quantum computers are being built right now which would perform all operations simultaneously, that everything is happening until you observe and it collapses, and they move. Transport of information inside of a computer is very, very significant contribution to time, but they are entangled, so it happens instantly. This is reality right now.